Sa video natin ngayon, we'll focus on the moment distribution method. Now, itong method na to, this is developed by Hardy-Cross, and then this method is also known as the stiffness method. Now, in order to solve problems using itong moment distribution method, we first need to know kung ano yung fixed end moments. Now, usually, we call this FEM. Now, we already have derived formulas para sa mga FEM ng common loadings natin. So, if we have a concentrated load P na nasa midspan, yung FEM will be PL over 8, and then dito will be PL over 8 then. Now, itong nasa left side, if this is, let's say, AB, ito yung FEM AB. And then itong sa kabila, this is FEM BA. Or simply, yung unang letter dito is kung saang point siya nag-a-act. And then dito rin, since nasa B yan, ito yung first letter. Now, if yung P is applied at the distance A, ito yung fixed end moment natin. PAB squared over L squared. And then dito sa kabila, that will be PA squared B divided by L squared. Now, hindi all the time mas malaki yung B kesa sa A. There are also cases na mas malaki yung A kesa sa B. And so yung mangyayari, the same lang din yung formula kasi this is already derived. And then if we have a triangular load patungo sa height, yung fixed end moment is WL squared over 20. And then dito sa 0 na point, yung fixed end moment natin is WL squared over 30. Now, diba, this makes sense naman kasi WL squared over 20 is larger than WL squared over 30 kasi mas malaki yung load dito compared dito. And then if you have a triangular load na symmetrical, then ito yung fixed end moment natin, 5WL squared over 96. And then kung meron naman tayong applied moment at any point, let's say at a distance A from the left fixed support, ito yung fixed end moment natin, MB over L squared times B minus 2A. And then dito naman, that will be MA over L squared times B minus 2A. And then kung meron tayong distributed load na applied at a certain distance lang, not at the whole span, or not over the whole span, medyo mahaba yung formula natin. But don't worry kasi bihira lang naman to lumalabas sa board exam. And then also, if we have a distributed load over the whole span, we have WL squared over 12 as the end moments. However, you have to take note of this. Yung conventions natin sa moment distribution method is yung counterclockwise positive and then yung clockwise negative. And so that means that this is positive because this is counterclockwise. And then this is negative because this is clockwise. And so dito ka dapat careful. However, in most cases, itong tatlo lang yung dapat mong i-memorize. Kasi ito yung mga pinaka-common. And then itong triangular load din pala. Or sometimes, lumalabas din to. But for concentrated load P, just memorize this one. Kasi applicable lang din naman to dito. However, our A will be L over 2. And then our B will also be L over 2. We can still get this formula. It's better to memorize this one para isa na lang yung i-memorize mo. And so since tapos na tayo sa fixed end moments, dito naman tayo sa distribution factors. Now, ito yung formula ng distribution factor. K divided by the summation of K. Now, sir, what do you mean by the summation of K? Yung summation of K, at some points kasi, especially sa interior points, we have to consider dalawang stiffness. Now, itong K dito, this is the stiffness of a member. And then, itong summation of K for interior supports, or let's say, we have this one, merong hinge dito, and then dito roller, and then dito is another roller. Let's say this is A, this is B, and this is C. Now, for member AB, we have KAB for this side, and then for this side, we have KBA. And then for member BC, for this side, we have KBC. And then for this one, we have KCB. Now, yung value ng KAB saka KBA, the same lang yan. And then yung KBC saka KCB, the same lang din. Now, let's say we have to compute the distribution factor of B at this point. Now, that will be KBA, which will be our K, divided by the summation of K. So, that will be KBA plus KBC. So, diba, itong B, meron tong dalawang distribution factors. Kasi dalawa yung adjacent spans. So, for this side, we have KBA over KBA plus KBC. And then here, we have KBC over KBA plus KBC. Ito yung mangyayari. Now, dito, the first letter of the point still applies. Kaya, this is B, kasi this is point B. And then, since this is considering span AB, letter A is our second letter. And then, dito naman, we have B. And then, since we are considering span BC, this is letter C. However, we have to take note of this. For fixed supports, yung distribution factor natin is 0. Kasi dito sa fixed supports kasi, walang rotation na mangyayari. Or, simply, 0 yung rotation or slope. And then, for exterior hinged or roller supports, yung distribution factor natin will be 1. Now, sir, ano yung exterior hinged or roller supports? Yung exterior hinge or roller support, that will be this one. and also this one. Kasi diba, itong hinge, this is at the leftmost part of the beam. And then itong roller, it is at the rightmost part of the beam. And so that's why we call it exterior. And then for fixed supports naman, our DF is 0. So DF equals 0 here, and then this is DF equals 1, and then ito rin. By the way, yung K pala dito, it's computed by this formula. We have 4EI divided by L, where E is the modulus of elasticity, I is the moment of inertia, and then yung L is the length of the segment or span. And so let's just say this is 5 meters, and this is 6 meters. Our KAB will be 4 times E. Let's say our E is constant. This will be 4E times I. Now let's say yung I dito is 1.5I for the 6 meter span. And so this will be 4EI divided by L, which is 5. For KAB. Now for KBC, we have 4EI, but our I is 1.5I. And so this is 1.5. And then divided by L, which is 6 meters. So this will be 6. And so ito na yung member stiffness natin. However, in our calculations, itong EI, usually magka-cancel yan. Kasi essentially, we are just taking the ratios, and then in most cases naman, yung E natin is constant all throughout the beam. And so essentially, itong distribution factor natin is a constant value, or unitless. Now, let's first discuss the steps kung paano natin i-analyze yung beam using this method. Now, yung first natin gagawin is we will solve for the distribution factor. But we can solve for this if we have the values of K, which I discussed earlier. Ito. And so once masasolve mo na yung DF, ilalagay mo dito yung mga FEM, or the fixed end moments at each segment. So for AB, you have FEM EB, and then for B, you have FEM BA, which are the following. For this example, we have PL over 8, and then for FEM BA, we have still PL over 8. And so ito yung ilalagay mo dito. And then once nalagay mo na to, you will multiply this moment by the distribution factor. And then yung product nila, ito yung ilalagay mo dito. Now itong orange pala na underline, ito yung sum of moments at a point multiplied by DF. Or simply, yung tawag natin dyan is unbalanced moments. So let's say, for this one, this will be FEM EB multiplied by the distribution factor. However, we have to remember that we'll multiply the FEM by the negative of the distribution factor. And so yung mangyayari dito, we will multiply the 2, but we will consider this as negative. And so this will be FEM EB times negative DFAB. Ito yung value natin para dito. However, if we are at an interior point, like for this ruler at B, diba, we have two values of DF. And so what we will do here is, to get the unbalanced moment, we have to add the moments at the same point. And so here, we have to add FEMBA and FEMBC. And then yung sum nito, ito yung imumultiply natin sa DFBA saka DFBC. Now let's say this expression is FEMABC, yung sum nitong dalawa. Now what we will do here for the unbalanced moment, we will multiply FEMABC by the negative of DFBA. So this will be FEMABC multiplied by negative DFBA. And then here, we have FEMABC multiplied by negative DFBC. Again, itong FEMABC, ito yung sum ng FEMBA saka FEMBC. And then dito naman, we'll just simply multiply FEMCB by the negative of DFCB. So this is FEMCB times negative DFCB. Yan. Now, if meron ka ng unbalanced moments, that will establish a cycle or iteration. So this is our first cycle. Now, once we establish our first cycle, what we will do next is we will carry over the moments. Again, itong purple na underline, ito yung carry over moments natin. And then to carry over a moment, alternating yung mangyayari. And so yung unbalanced moment dito, we will divide that by 2, and then andito na yan. So this is essentially FEMAB times negative DFAB divided by 2. That's how we will carry over moments. And then ito, this will be FEMABC times negative DFBA divided by 2. And then ito naman, this will be FEMCB times negative DFCB divided by 2. And then here we have FEMABC times negative DFBC divided by 2. And then once we get these values, babalik tayo sa process na to. We will multiply this by DFAB, and then ito na yung ilalagay natin dito. And then we will take the sum of these, and then we'll multiply that by DFBA for this one, and DFBC for this one. And then here, we will just multiply the carryover moment by DFCB, or the negative of DFCB. And so here, meron ka ng unbalanced moments, so that will be your second cycle. And then next, you will carry over the moments, and then you will repeat the process until yung unbalanced moment will be virtually 0. And so here, again, we'll multiply the moment carried over by dFA and then repeat the cycle until the carried over moments multiplied by the distribution factor will be equal or approximately equal to 0. So let's say, dito sa unbalanced moments mo, you have a value of 0 and then dito 0.002 and then dito 0.001 and then here meron kang 0. These are virtually equal to 0. And so that means that you can stop the cycle. And then once you will stop the cycle, you will actually add all the moments from FEM-AB up to this point. And so once you add all those moments, yan na yung moment at a point. For example, yung sum ng moments dito, this will be the moment right here. And then yung sum ng moments dito, again, since this is the same point, itong values mo dito sa moment or yung sum nitong lahat should be equal. Kasi diba at the same point, the same yung moment natin. And so these should be equal. However, although itong dalawa are equal, dapat opposite yung signs nila to maintain equilibrium. And then we will also get a moment here. And then yung sum ng lahat ng to will be the moment right here at C. However, since we have an exterior support at C, magzi-zero lang yung moment dyan. Now, in cases where we have an exterior hinge or roller support, we can actually simplify our calculations by multiplying the stiffness index or K by 3/4. Ito yung alternative or shortcut. Now, we will multiply the stiffness index by 3/4 so that we can get a modified value of K. Now, if gagamitin natin yung modified factor, we will actually stop at the first cycle kung saang point ginamit mo yung modified factor. Like for example, since at C, meron tayong external ruler, if we'll use the modified factor, we will actually multiply KCB by 3/4. And then ito yung value na gagamitin natin dito. And then if you will use the modified factor, dito sa first cycle, you will already stop. And then yung mangyayari is malalock na to. Or simply, you will just carry over the moment directly after the first cycle. Now, I will show this to you later kung paano to i-apply. Now, sir, what if apat yung supports? Ito yung mangyayari. For all interior supports, we have 2 distribution factors. And then for the end supports, we only have 1. And so if you will carry over the moments, ito na yung itsura. And then essentially, you will just stop kung yung unbalanced moments will be virtually equal to 0. And then if we have 5 supports, ito yung carry over moments natin. Or yung pattern ng carry over moments. Now sir, what if merong free end? Ano yung mangyayari? Now meron akong note dito na if we have a free end, we will not have a distribution factor. However, the moment at CD dito can be directly computed. And so yung moment sa CD, take note na what we are considering is the reactive moment at CD. So for example, if we are to compute MCD, this is supposed to maintain equilibrium. Now diba, taking moments about C, we have P times LCD, or the length of CD. Now diba, this will cause a clockwise rotation about C. And so that means na yung reactive moment natin dito will be counterclockwise to oppose this one. And so this is MCD. And then diba, in our conventions, if we have counterclockwise, that will be positive. And so this is how we can compute MCD. However, what's going to happen here, if we have a free end, is we can just actually neglect this portion and then we'll just add FEMCD right here. And then we won't have any distribution factor at this point. Kasi we can just actually cut this one. And then yung moment na makukause ng P, we'll transmit that dito. And so essentially, this will be the same sa first example. Or itong case na to, in which meron tayong fixed support and then merong dalawang rulers. Isang interior and isang exterior. And since meron na tayong exterior ruler, we can actually use the modified K, yung imumultiply natin sa 3/4. Now, para ma-internalize natin yung discussion, we'll actually solve a sample problem. Now, we have a beam, ABCD, wherein varying yung moment of inertia. Kasi dito sa AB, we have I, and then from B to D, we have a different I. And so that's why this is larger than AB. Now, diba, as discussed earlier, if we have a free end, we can actually transmit the moment. And so this is 40 kNm clockwise. And so that means dito sa point B, we'll have a reactive moment. And then ililabel natin to as MBA. Now our MBA will be 40 kNm to maintain equilibrium. So this is 40 kNm. And so diba, if we are able to transmit this moment, we already know the value of the moment dito. And so we will just actually exclude this portion, itong AB. And then we'll just consider beam BCD. But itong 40 kNm, this will have a bearing sa calculations natin. Kasi this will be added to the fixed end moment at B, considering BC. Meron kasi itong moment dito, and then meron din itong moment dito. Different for the adjacent span AB, and different for the adjacent span BC. Now first, we'll compute the FEM. And so diba, itong BC, this has a concentrated load at the midspan. Kasi this is 2 meters and this is 2 meters. And so diba, we have B and then this is C. And then this is FEMBC while this is FEMCB. Now diba, sa conventions natin, yung counterclockwise is positive and then yung clockwise is negative. And so our FEMBC will be positive. And then yung P natin is 200 kN. So this is 200 and then we have PL over 8. So 200 times the length, which is 4 meters, divided by 8. So this will be 100 kNm. And then for FEMCB, we still have the same value, but yung moment natin will be negative. So this is minus 100 kNm. Again, this is already 100 because the same lang yung magnitude nito. And so let's just move this one. Maybe dito. Now, dito na naman tayo sa CD. Now, diba, we have a triangular load. And so, balik tayo dito, we can actually use this one. And so, since we have the same orientation, ito na lang yung gagamitin natin. So, diba, this is 6 meters, yung length ng CD. And so this is point C and this is point D. And then yung load natin is 10 kN per M. And so diba, we have this formula. And so our FEMCD will be, since this is counterclockwise, that will be positive and this is negative. So FEMCD will be 10, which is W, times L squared, which is 6, divided by 20. So this is 18 kNm. And then for FEMDC, which is this one, we have WL squared divided by 30. But this is negative, so this will be negative 12. And so let's just move this here. Now first, we'll actually compute K. Again, we have the following formulas. So copy na lang natin. And then here, we'll compute DF. And so diba, essentially, yung nangyari, ito na lang yung beam na kinonsider natin. So let's just copy this one. And then we'll erase this portion. And so this is what's going to happen. And then now, we can construct our table. But first, we'll first accomplish this. Now diba, for exterior hinged or roller supports, our DF is equal to 1. And so dito, our DFBC will be equal to 1. Yan. And then likewise, our DFDC will also be equal to 1 kasi this is an exterior hinge. And so yung isosolve natin na DF will be for this interior support. Now diba, computing KBC, we have 4EI over L. So this is 4 times E times I divided by the length, which is 2 meters plus 2 meters, that will be 4 meters. And then for KCD, for this adjacent span, we have, again, this is just the same with KCB kasi equal lang naman yung values. Let's just actually change this into KCB. And then our KCD is equal to 4EI divided by the length, which is 6 meters. By the way, our I is 2I. So this is 2I and this is also 2I. However, hindi to magmamatter kasi constant yung dalawang I. Or simply, the same yung moment of inertia ng BC saka CD. And so later, itong 2I will just cancel. So you can just actually write this as I and this one as I if constant yung dalawa. Now first, let's compute DF of CB. Now DFCB will be KCB divided by KCB plus KCD kasi this is the summation of K. And then our DFCD will be KCD divided by KCD plus KCB. Now diba, for KCB, this will just cancel and then we have 2EI. And so this will be 2EI and also this one. And then for KCD, we have 4 times 2, that'll be 8. And then 8 divided by 6, that'll give us 4 thirds. And so this will be 4 thirds EI or 4EI divided by 3. And so this will be 4 thirds EI. And then ito naman, this will be 4 thirds EI divided by 4 thirds EI plus 2 EI, which is our KCB. And so diba, since all expressions contain EI, we can just factor EI out. And then diba, magka-cancel lahat ng yan. So this will cancel, and then ito rin. So we can just use the constant values. So for DFCB, we have 2 divided by 2 plus 4 thirds. Now that'll give us 3 over 5, which is 0.6. So this is 0.6. And then our DFCD will be 4 thirds divided by 4 thirds plus 2. Now that'll give us 2 over 5, which is 0.4. Now yung sum ng dalawang to, if we have an interior support, that should be equal to 1. Now diba, 0.6 plus 0.4, that gives us 1. And so tama yung DF natin. And so now we'll draw the table. Let's draw a line here, and then dito, and also dito. And so this will be DFBC, which is 1, while this is DFCB, which is 0.6. And then here we have DFCD, which is 0.4. And then dito sa point D, we actually have DFDC, which is also equal to 1. And so this is 1. And then next, we'll write our FEM. Now FEMBC is equal to 100 and FEMCB is negative 100. So we have 100 and negative 100. And then our FEMCD is equal to 18 and then our MDC is equal to negative 12. And so this is minus 12. Now diba, this is CB and then this is for CD and then DC, BC. However, dito usually nagkakamali yung mga students. Kasi diba, when constructing the table, hindi na nila sinasali yung MBA. However, diba, since we have cut this portion, itong AB, then yung reactive moment dito should also be included. And then diba, we have established that it is counterclockwise. And so essentially, we have BA right here. And then we have a moment of 40 kNm. So this is actually 40. Now diba, first, we need to get the unbalanced moment. So let's color this orange, and then dito rin, and then here. So these are our unbalanced moments. And so diba, to get the unbalanced moment, we have to add the FEM of 1 point and then multiply it by the negative of the F. So diba, yung sum ng 100 saka 40, that will be 140. And so 140 times negative 1, that will give us minus 140. And so here we have our unbalanced moments. And then for joint C, we have minus 100 plus 18, that will give us minus 82. And then diba, negative 82 times negative 0.6, that'll give us 49.2. So this is 49.2. And then multiplying by negative 0.4, we have 32.8. So this is 32.8. Again, we are multiplying the sum to the negative of the F. Yan. And then by the way, na-erase yung FEM dito. This is supposed to be 12. Negative 12. And so negative 12 times negative 1, that'll give us positive 12. And so this is plus 12. Now diba, the moment at AB is known. So that means that our unbalanced moment here will be 0. Kasi we don't need to balance this one. We'll just actually treat the unbalanced moment of AB as 0. And so diba, we're just essentially analyzing BCD. So yung carryover natin will be alternating for these points. And so let's draw our lines for the carryover moments. So we have purple, and then these are our carryover moments. And so diba, we will divide by 2 and then alternating. So negative 140 divided by 2, that will give us minus 70. And then 49.2 divided by 2, that will give us 24.6. And then 32.8 divided by 2, that will be 16.4. And then 12 divided by 2, that will be 6. And so now, this establishes our first cycle. Again, our cycle is counted with the unbalanced moment, not the carryover moment. And so for the second cycle, let's just actually copy this one. And so we have another set of unbalanced moments, which is our second cycle. However, to get this one, we'll actually use the carryover moments. Now 24.6 times negative of df, which is 1, 24.6 times negative 1 will be minus 24.6. And then minus 70 plus 6, that'll give us minus 64. And so minus 64 times negative 0.6, that'll be 38.4. By the way, this essentially has 0 right here. And so the sum of these will just actually be this value. And so that's why this is 24.6 times negative 1, and then this is minus 24.6. I hope that's clear. And then here we have minus 64 times 0.4, that'll be 25.6. So 25.6. And then here, 16.4 times negative 1, that'll be minus 16.4. And then we'll carry over the moments. So we will divide this by 2. Now minus 24.6 divided by 2 will give us negative 12.3. And then 38.4 divided by 2, that'll give us 19.2. And then 25.6 divided by 2 will be 12.8. And then 16.4, minus 16.4 divided by 2 will be minus 8.2. And so let's do another cycle. And so we'll compute new unbalanced moments. So our unbalanced moments will be, for this one, we have 19.2 times negative 1. That'll be minus 19.2. And then minus 12.3 minus 8.2, that'll give us minus 20.5. So this is minus 20.5. And then minus 20.5 times negative 0.6, that will be 12.3. So this is 12.3. And then times 0.4, that will be 8.2. And then 12.8 times negative 1, that will be minus 12.8. And so carrying over our moments, we have minus 6.15, and then minus 9.6, minus 6.4, and then 4.1. And then for the fourth cycle, we have will be minus 6.15 times negative 1, that'll give us 6.15. And then we need to get the sum of these. And so minus 9.6 minus 6.4, that'll be minus 16. So minus 16, and then multiplying that by minus 0.6, this will be 9.6. And then multiplying that by 0.4, we have 6.4. And then 4.1 times negative 1, that'll be minus 4.1. And so diba, you can notice a pattern right here. This is minus 12.3, and this is 12.3, and then minus 0.6 and 9.6. In the same way, this is minus 8.2 and positive 8.2, and then minus 6.4, then positive 6.4. So essentially, if you add all of these, they will just be 0. And so diba, that means that we can actually end here. Because although our unbalanced moments did not approach 0, yung values kasi are already alternating. And so if I will add all of these, they will just be 0. And so I can just actually stop right here. And so let's just erase this one because we don't need to carry over. And then we will end at this cycle. And so once you will be able to determine that you will stop the cycle, you will add all of these values from the FEM. So diba, for this column, we have 100, which is this one, and then minus 140. And then we'll just exclude these. Kasi diba, alternating lang naman yung signs. 24.6 minus 24.6 will be 0. 19.2 minus 19.2 will also be 0. So we will neglect these. So 100 minus 140, this will be minus 40. So we have minus 40. This is our MBC. And then here we have minus 100 and then plus 49.2 minus 70 plus 38.4. That'll give us minus 82.4. So this is minus 82.4 for CB. By the way, we are excluding these kasi alternating na yung values. And then here we have 18 plus 32.8 plus 6 and then plus 25.6, that'll give us 82.4. So this is 82.4 and then positive. And then this is for MCD. And then here, since the values are just alternating, the sum of that will be 0. So this is MDC. And then diba, this makes sense naman kasi this is an exterior hinge support. So the moment there will be 0. And so we will now use these values so that we can solve the reactions. And so now, we'll actually bring back span AB para ma-analyze natin yung whole beam. So we have AB, which is 3 meters, and then we have an applied moment, which is 40 kNm. However, take note that itong 40 kNm, this is the moment at BC. So this is actually an internal moment. So let's first remove this one. Now, yung next na gagawin natin is we'll separate the segments. First, we have AB, and then we have BC, and then we have CD. Now, at each segment, kailangan natin i-maintain yung equilibrium. So diba, at each point, we have shear forces and internal moment reactions. So we have dito, the shear at A, and we have the shear at B. Or let's just say this is VAB, and this is VBA. And then dito sa BC, we have the shear of BC, and here we have the shear of CB. And then this will be the shear of CD, and this is the shear of DC. I hope you agree with this one. And then next, we'll apply these unbalanced moments. And so ilalagay natin yan per point. So sa BC, we'll put negative 40. Now since this is from our table, yung negative 40, magiging clockwise. So this is clockwise, clockwise, counterclockwise since positive. And then this will just be 0. Or simply, wala tayong moment na ilalagay dito. By the way, itong FBD na to, this is looking at the beam internally, not externally. However, ginawa ko na lang upward yung arrows so that we'll just add them when we go to the reactions. And so, analyze internally. So, diba, dito sa AB, we have a moment of 40 kNm. So, this is 40 kNm. And then to resist this one, at B, we need to have a reactive moment, which is MBA. So, this is 40 kNm. Now, this is just the same with this one, MBA. So, this is MAB, and this is MBA. Now, let's just move this, and then let's space this one. Yan. Now, diba, since we don't have vertical forces here, only moments, our VAB and VBA will just be equal to 0. So, this is 0, and this is also 0. And then next, for BC, we'll include the concentrated load. And so we have 200 here. And then this is 2 meters, as well as this one. Now here, we have MBC, and then we have MCB. Now our MBC is equal to negative 40, which is clockwise. So equals 40. And then for CB, we have minus 82.4, which is clockwise. And so this assumption is actually wrong. So this is clockwise. And then we have a value of MCB equals 82.4. And then for span CD, we have 82.4 but counterclockwise. So this is counterclockwise MCD. And then for MDC, we have a moment of 0. And so now, we'll solve the shearing forces. because it's what we need in order to solve the reactions. Now take note here that when we will apply equilibrium equations, the conventions here, which is counterclockwise positive and clockwise negative, will no longer apply because you can just actually use another assumption. Now since what I'm used to is positive is clockwise and negative is counterclockwise, I will just use this one. And so analyzing span BC, we can take moments about C in order to solve VBC. So we have summation of moments at C, that'll be VBC times 4, and then plus 40 because this is clockwise, and then minus 200 multiplied by 2, and then plus MCB because this is clockwise, so plus 82.4. And so solving VBC, we have 4x plus 40 minus 200 times 2 plus 82.4 is equal to 0. And so this is 69.4. And then this is upward. And the next, we'll solve VCB. Now to solve VCB, I will just sum up forces vertical. So I have summation of Fy equals 0, which is VBC minus 200 plus VCB. And then this is equal to 0. However, I know that VBC is equal to 69.4. And so 200 minus 69.4, that'll be VCB, which is 130.6. So VCB equals 130.6. And then this is upward. And so this is 69.4 while this is 130.6. And the next, we'll analyze span CD. Now on span CD, we have a triangular load. So this is 10 kN per m, and then here we have 0. And so since we have a triangular load, we have a resultant right here, which is the area of this triangle. Now that'll be 1/2 times the base, which is 6 meters, multiplied by the height, which is 10. So this will cancel, this will be 3, and then 3 times 10 will give us 30. And so to get VCD, I can take moments about D. Now by the way, our MCD is equal to 82.4, and then counterclockwise. So this is 82.4. And so summing up moments about D, we have VCD times 6, and then minus 82.4 because this is counterclockwise, and then minus 30 multiplied by the moment arm, which is 2/3 of 6, and then plus MDC, which is just 0. So exclude na lang natin. So equals 0, we have 6x minus 82.4 minus 30 times 2/3 multiplied by 6 equals 0. Solving x, we have 33.73. So VCD equals 33.73. And then this is Kn. Yan. And then to solve VDC, we can sum up forces vertical. And so we have VCD, which is 33.73 minus 30 plus VDC is equal to 0. And so our VDC will be minus 33.73 plus 30. And so this will be minus 3.73. And so yung negative sign, that means na mali yung assumption natin. Instead of upward, VDC is actually acting downward. So this is downward. And so ito na yung shear values natin. Now sir, ano yung next step? Para makuha natin yung reactions, we will actually add the shear forces at each point. Now diba, this is point B, and this is also point B. And so that means na yung BY will be 0 plus 69.4 kasi these are both at point B. So our BY is 69.4 kN. And then for point C, we have CY is equal to 130.6 plus VCD, which is 33.73. So this is 33.73, and then adding both of these, we have 164.33, and then this is Kn. And then for VDC, we have negative 3.73, and then this is Kn. However, since this is negative, then our assumed direction is actually wrong. And so if we'll consider the whole beam, we have the following reactions. At B, we have 69.4, and then at C, we have 164.33, and then lastly, dito sa D, we have dy, which is downward because this is negative. So dy is acting downward, and then we have 3.73 kN. And then our horizontal reaction for the hinge will just be 0 because we don't have any horizontal forces. And so ito na yung mga sagot natin. Now, there's actually an alternative to this problem, which I did not discuss earlier for the intention that I will be demonstrating it here. Now, this shortcut applies if you have a two-span continuous beam wherein both ends have exterior hinge or roller supports. Now, diba, this beam meets that condition kasi this is a roller support exterior and this is a hinge support that's exterior. And so now, tuturuan ko kayo sa technique dito. Now, instead of doing these steps, itong ginawa natin kanina wherein kinuha natin yung unbalanced moment and then nag-carry over tayo, dito, we will actually first balance itong mga nasa far end or itong mga nasa exterior na support. So, diba, first, we will get the sum of these. Kasi ito kasi yung total moment na kinikarry dito, or yung fixed end moment. So, 100 plus 40, yung sum niyan will be positive 140. Now, let's just actually move this. Yan. And then yung mangyayari, ito yung first nating ibabalance. Later na natin to gagawin. And so, what's going to happen is, we'll first multiply this by the negative of df. So, diba, our unbalanced moment will be 140 times negative 1, which is minus 140. Now, yung sum dito, I'll just move that here so that you'll be able to know that this will not be part of what we will sum up later. So, diba, itong 140, this is just the sum of 140. And so, that's why, nandito yan sa gitna. And then, yung negative 140 just comes from 140 times negative 1. And then here, for the unbalanced moment, dito sa DC, we have negative 12 times negative 1. And so, diba, that will be positive 12. Now, yung mag-iiba dito is we'll actually carry over this moment and also this one. We will not yet do this one. And so, diba, if we'll carry this over, we have dividing this by 2, magiging negative 70. And then here, dividing this by 2, this will become 6. And so our next step will be to add both of these. And so we'll be able to get another value. So this will be minus 100 minus 70, that'll be minus 170. And then 18 plus 6, that'll give us 24. Now itong values dito, this will be our new FEM. This is what will happen. And then essentially, we'll add both of these and then multiply by df so that we can get the unbalanced moment. So we have two unbalanced moments for this one and this one. Now this will be minus 170 plus 24, that will give us minus 146. So this is minus 146. So minus 146 times 0.6, that'll give us minus 87.6. And so we have minus 146 times negative 0.6, that'll give us 87.6. So 87.6. And then multiplying by negative 0.4, we have 58.4. So this is 58.4. Now diba, we have exterior supports dito, sa B, sa D. And so that means that our carryover moment will just become 0. Yan. And the next, if we'll get the unbalanced moment, diba, yung sum nitong dalawa, that will become 0. And so diba, 0 times negative 0.6, that will just be 0. And then 0 times negative 0.4, that will also be 0. And so that means that we can stop our cycle. Kasi diba, yung unbalanced moment natin is already 0. And so let's just actually sum up all of these. However, take note here that we'll sum up from the new FEM, not from this one. Because yung ginawa natin is we carried over these moments directly. So, negative 170 plus 87.6, we have negative 82.4. So this is minus 82.4. Now this is our MCB, or I'll just put this here. This is MCB, and then for MCD we have 24 plus 58.4, that will be 82.4 positive. And then for MBC, which is this one, we have our FEM, which is 100 minus 140, which is our unbalanced moment. So minus 140, that'll give us minus 40. So this is minus 40. And then here we have our FEM is negative 12. Now minus 12 plus our unbalanced moment, which is 12, that will become 0. And so that's why this is 0, our MDC. And so notice that this is just the same earlier, wherein our BC is negative 40, our CB is minus 82.4, CD is 82.4 positive, and then DC is 0. So this is how you can apply the shortcut if you have two spans, and then both exterior supports are hinges or rulers.